Hello, good afternoon, and welcome to this webinar of new developments in Siesta for high-performance material simulations. My name is Emilio Artacho, and this is a webinar offered by the MAX European Center of Excellence. It is actually within a series of seminars that has been and will be showing you the new developments or recent developments of the flagship codes supported in this Center of Excellence. Actually, I'm going to take the opportunity of advertising the next one, which is going to be on the 14th of October on the FLIR code as well. So, but back to this one, here you can see the speakers today, and left to right are in the order of the different mini talks that you're going to be hearing within the webinar. So I'm the first one on the left, Emilio Artacho, and we'll be giving you a little bit of an overview of the Siesta code. Then Alberto will tell you much more about the developments of new solvers. Pablo Ordejon will tell you a bit about TranSIESTA and what it does, an overview about it, while Nick Papier will tell you much more on the technicalities of the new developments of it. And we are going to end up with Mónica Garcia Mota, who is going to tell you a little bit about the support of the Siesta community through Simune's effort. Simune is a company in San Sebastian, but very much engaged with that kind of support that Max is doing. So getting into my own talk, it's going to be about an overview of the Siesta code. And as you probably, most of you will know, Siesta itself is a density functional theory code. It is like many others in many ways, but from its very inception, Siesta was aiming for efficiency. So it was a code that was devised in order to be able to do density functional theory calculations much more efficiently. And efficiently means you can do larger simulation boxes, pack in more atoms of different kinds, and that opens applicability to lots of different kinds of contexts and complexities. So that's a reason for the efficiency at the time. And actually it was the very first fully self-consistent linear scaling density functional theory code in the 90s. And linear scaling meaning that the computational effort, both in CPU and memory, would scale with the number of atoms instead of the cube of the number of atoms. That is the conventional scaling for density functional theory complexity in the codes. So the Siesta code is based on atomic orbitals that are used as basis sets. And it is something which is very conventional, for instance, in traditional quantum chemistry. It's nothing new. And these atomic orbitals are constituted by functions that are the product of a radial shape and an angular shape for this functional. The angular shape is just spherical harmonics of the kinds that you're probably familiar with, SP, PX, PY, PZ, and so on and so forth. And the radial shapes, will come back to them in a moment. So the disadvantage of this kind of scheme is that convergence with basis set is much more laborious. It's not systematic or automatic as you could do it with things like plane waves. And it is responsibility of the user to choose the right basis set for your problem, your system, the kind of accuracy you need, and so on and so forth. And so it's, again, more laborious and less automatic. But it has as an advantage, a key advantage is that you need much fewer basis functions per electron are needed. And that impinges a lot into the efficiency of the calculations. Rule of thumb, as I have here, is that you may need of the order of 3-5 functions per electron for the calculations for which you would need of the order of 100 plane waves per electron. So since these numbers affect very much the sizes of the matrices you have to, for instance, diagonalize, then that's going to impinge very clearly into the efficiency of the code. Again, not new, and many other codes are using similar technologies of atomic orbitals as basis sets. Of course, most of the quantum chemical ones, and you have here some of them, QChem, NWChem, ADF, Gaussian turbomol, but also some that come more from the physics community, like DMOL, FIA, AIMS, CP2K, that are codes you may know, in addition to Siesta. Now, going a little bit more to the peculiarities of Siesta itself, and actually of the Siesta method, we are going to be using finite support for the basis functions. And that is the radial shapes that I was talking about for the atomic-like orbitals. They're going to be such that they are actually confined strictly within a radius from the center of that orbital. And from then on, they are strictly zero, as compared with traditional basis sets in which there was a decay, but the decay would not really go strictly to zero up to infinity. That means that the matrices we're dealing with are going to be strictly sparse. We won't need to neglect or cut matrix elements a posteriori. Actually, the zeros in the matrices are going to be exactly zeros. And as long as, this is a key point in Siesta, as long as you have finite support basis functions with a radial time spherical harmonic shape, the rest is up to you, the user. You can put as many as you want, whatever you want, and of any radial shape you want. In this instance, I normally say that if you want to put the New York skyline as your radial shape, is your problem. You can do it if you wanted to, and if it's good for your calculations. So using that, let me state, for instance, let me put it in as the two key components from the computation point of view of a typical density functional theory code. You have one bit in which, given a density, particle density, electron density in your problem, you compute the Hamiltonian for your particular problem, the Consham Hamiltonian. So the computation of the matrices and matrix elements, when you have the finite support I was talking about, together with a discretization of space, here you have a cartoon, your finite support basis functions in 2D, and discretization of space. Actually, once you convert this into lists and sparse matrices, you can get to algorithms that would be absolutely always linear scaling and computational effort. So the calculation of the Hamiltonian and overlap matrices are always linear scaling within Siesta. And that was from the very beginning of the Siesta method. And that is a key for the efficiency of the Siesta code. Then there is a second step, which is, given the Hamiltonian matrix and the overlap, you want to get the energy and the density itself, that is solving the Consham eigen problem. Originally, Siesta was devised with linear scaling solvers that were based on localization of solutions. So here, again, on a cartoon basis, if you have these smaller circles, filled circles as the pseudopotentials, if you want, the ions, and then the bigger one, the slightly bigger ones are the finite support region for the basis orbitals. You have a much bigger ones, the solution wave functions that we're after. You can think of them as Vannier-like solutions of your problem. Of course, that would be for insulating or semiconducting problems. That was everything we had at the very beginning of Siesta. Since then, it has evolved, and now we have many different solver options or various solver options, from linear scaling to cube scaling, involving conventional diagonalization of different flavors, and so on and so forth. But there will be a talk dedicated to that, so let me not expand much more on that. So once we had that kernel of the code at the very beginning, from very early on, the Siesta was offering typical things from DFT code. So you could use different kinds of GGAs, you could do first principles molecular dynamics, different kinds of relaxations, different analysis tools, and so on. And the early code and the details of the method are all explained in a key publication in the Journal of Physics Condensed Matter of 2002, Soler and other co-authors. And since then, it has evolved, and it has evolved substantially. And there is a recent account of the recent status in this other paper by Alberto Garcia and others in the Journal of Chemical Physics this last year in 2020. And here, let me just mention some of the developments. So there has been quite a lot of development for ballistic transport, ballistic electron transport through nanostructures in the TranSIESTA code, which is part of the Siesta package. There is also time-dependent DFT in real time. There is full spin orbit coupling with non-collinear magnetism, various eigensolvers with different scaling, as I was mentioned before, and Alberto will tell you more about. Density functional perturbation theory for phonons and other kinds of small perturbations in linear response. There is also multi-scale options, so having things like QMMM in bio settings or second principles calculations in large-scale materials calculations are also possible. Time-dependent density functional theory in linear response as a function of omega, and GW post-processing calculations on top of Siesta results is also possible now by things done, developments done on top of that by Daniel Sanchez-Portal and Peter Koval and others, and many other things in terms, for instance, of analysis tools and post-processing tools. The code itself developed gradually from a closed enterprise, but it opened up gradually, and it was open source for academics since around 1999. And it became fully open source in the GPL, under GPL license in 2016 for several reasons. And you can find the whole of the project there. So it is the trunk, the different releases, different branches with different things that are being implemented, and even branches of other possible people that are contributing to the project and are making their branches public. So all of that should be findable there. So concerning the usage of the Siesta code is extremely varied. I mean, in the moment you can put lots of atoms into a box, then there's quite a lot of simulations within the context of physics, chemistry, material science, bio context, geo, nano, even engineering. It is hard to follow what people are doing in the community, since we have of the order of 14,000 papers citing the Siesta core papers, around 1,000 a year. So you can imagine that there's quite a lot of variety in these things. Let me just illustrate it with some different examples close to the kinds of things we do. Here in the materials context, for instance, here I show a nice picture of large-scale material simulations of a ferroelectric paraelectric superlattice, in which you can see vortices of polarization within the ferroelectric, which is it was published a few years ago, and this involves several thousand atoms in the calculations, and it involves second principles for the simulations. So the bio context has been very much at the heart of the early Siesta development from the beginning, and the structure and electronic structure calculations of DNA at a full double strand of DNA was one of the early results of us ourselves within Siesta, with Siesta, as you can show there, but it has been applied to many other things. Here's another example here below, which is a pillin protein in wet conditions, and here there is electrostatics. That's an electrostatic map, but is a situation in which we have a natural evolved nanoelectric wire, which some strange bacteria are using to feed themselves. And so electronics is very important there, as well as the electrostatics shown here. So there were Siesta calculations, again, with, in this case, it was of the order of 4,500 atoms. And other completely different, but also interesting kind of example is this one in which we're looking at electronic transport. Both Pablo and Nick are going to talk about these things. This, let me just illustrate it. This is a 4-point contact, and you have electronic transport in this quite demanding situation, relatively recent calculation. So a little bit closer to my own work, we're doing very far from equilibrium simulations using time-dependent DFT in a similar way that you would do time-dependent Schrödinger equation. That would be the equivalent Kohn-Sham equation, but it is the time-dependent like. And what we're doing is shooting projectiles through solids, which generate very large energy transfer. So we're not talking about subtle energetics here. We're talking about many electron volts per angstrom along the trajectory. So we put a projectile into a simulation box and we kick it, and it moves across and generates all sorts of havoc. And this is what you're seeing here in this illustration of protons and germanium. And through that, we have been learning quite a lot of things related to this very highly non-equilibrium process. In particular, for instance, one can see things like that. This is the actually dissipation of this proton due to the electron excitations for protons in gold and alpha particles in gold. This is a comparison theory of experiment of the kind you're very used to and the kind of accuracies you're very used to with density functional theory. But in this case is a genuinely far from equilibrium quantity of which you don't see so many in the first principles context. So that has been quite pioneering as well. So there will be a little bit more on the re-engineering of the code towards exascale and so on. And Alberto will tell you more about that. This picture is, this figure is part of just transmitting about scaling with number of processors in different kinds of situations. And I'm just flagging it up for as an advance for next speech. But let me mention in this context something which again is close to my heart, which is we are re-engineering codes, and Max is very much at the heart of bringing electronic structure codes towards exascale computing, but we're not doing it in the old way. We're changing paradigm, and this is something that we have been pushing for some time, which is, if you see about this figure on the left, that would be the old way of doing things. You have an electronic structure code, which is monolithic in the sense that the whole code is being delivered as one single unity to be compiled and used, and it is based on relatively very, very basic and fundamental libraries. We're changing to this other new paradigm in which the electronic structure driver is in itself a part of a much more modular entity in which we're dealing with different kinds of things at different levels. Nuclear degrees of freedom would be here in purple, workflow tools, but we have heavy-duty electronic structure tasks that are being shared, developed, and re-engineered in a common basis for many different codes, making trying to avoid the reinventing of wheels every step of the way. So that is something which is happening both in the US, in the USA, and Europe. We're both pushing it, and actually in collaboration. Here you have just pictures showing, for instance, here the electronic structure library that has been pushed by CCAM, in which you can see probably codes that you have heard about. Here is Siesta, but also a Bennett, Octopus, FHA Ames, Quantum Espresso, Big DFT, that have been joining together in order to put together different kinds of, and extracting things, bits of codes that can be librarized, made libraries, and then shared and re-engineered themselves instead of re-engineering the whole code. Same here for the LC effort in the USA about electronic structure solvers. And in this context, let me just finish by mentioning this electronic structure library. It is, of course, bundled, trying to make it easy to use for the community, for people compiling it and so on. But quite a lot of the effort is actually by people that are now in Simune, the company I was talking about before, of which Monica will tell you a little bit more. And with that, I want to finish and give time for my colleagues to tell you about other kinds of things within Siesta. So thank you very much for your attention. And the next speaker could take control of the screen. So this is Alberto Garcia. Okay.
I forgot to unmute myself.
Okay.
Okay, this is Alberto Garcia. I'm going to tell you about one of the parts, one of the modules that Emilio was talking about in his transparency, the quantum engine, which is at the core of Siesta and is the calculation of the actual electronic structure. So Siesta uses a basis set of atomic orbitals. This is the typical one electron wave function that you can write in expanding in that basis. So you have some coefficients, and the standard way to get these coefficients is to solve this eigenvalue problem. It's called a generalized eigenvalue problem because it has these non-orthogonal feature, which is the overlap matrix. The orbitals are not orthogonal because they are localized and they're on different sites. So we need to take this into account. So once you build the Hamiltonian and the overlap matrix, you can get via diagonalization the coefficients. And then you can get the charge density, energies, etc. When you look at the charge density, for example, you will notice that it can be put in this compact form with these coefficients, which are built from the coefficients of the expansion of the wave functions and the occupation of the states. This is called the density matrix, and it's an object which features prominently in the Siesta inerts. As Emilio said, the solver step takes most of the CPU time because the building of HNS is linear scaling and has a low complexity because of the localized character of the Siesta basis. So, when you stop and think of how you go about solving this problem, the first idea, and this was done traditionally in Siesta, apart from the original linear scale solver, which Emilio mentioned, you need to invoke some kind of mathematical routine to solve a very well-defined mathematical problem, which is a diagonalization. So in Siesta, we have used prepackaged libraries traditionally. For example, Scalapack. And typically, I should say that these are direct solvers as opposed to iterative ones, because the number of desired eigenvectors is a substantial fraction of the matrix size. Since in Siesta we have very few basis orbitals, the cardinality is low, the size of the matrix is not too much larger than the number of occupied states. So that forces us to use direct solvers, which are typically a sequence of steps. One would, for example, first start by converting H and S to dense form, then performing a Koleski decomposition to reduce to the standard eigenproblem, transform to an easier kind of matrix to handle, in this case a tridiagonal form, solve it in this tridiagonal problem, and then back transform. These things are typically encoded in these drivers from Scalapack, and these are the traditional ones used in Siesta. We have also offered more recently other solvers in the Scalapack. Then more recently, we have implemented an interface to the ELPA library, which offers an optimized experience compared to Scalapack. It has a different sequence, taking the original matrices to the tridiagonal form, and it's more efficient and scalable. Still, this approach to solving the electronic structure problem has cubic scaling with matrix size, and is quadratic scaling for memory because of this dense form of the matrices. Still, since Siesta has such a small basis set, it's very competitive with other codes. So this is more or less the standard way of doing things in Siesta with regard to solving the electronic structure problem. Now, there is another alternative, which is to use a formal relationship between the density matrix and the Hamiltonian. Basically, the density matrix can be seen as the application of the Fermi-Dirac function on the Hamiltonian. And the trick here is to choose an appropriate form for the Fermi-Dirac function that can be used in linear algebra. One of the first ideas was the Fermi operator expansion, which is to turn this into a polynomial series. And then all you need to do is to perform multiplications to get the density matrix. Since the matrices involved are sparse, this is a procedure that is linear scaling. This has been implemented in the chess library, which was originally part of Big DFT, that has been made into a standalone library and also ported to Siesta by Stefan Moore from the Barcelona Supercomputer Center. So this is another linear scaling addition to the Siesta repertoire. Is not very much used still because we are working towards enhancing even more its performance by exploring on-the-fly construction of the basis set. Because the number of terms in this expansion depends ultimately on the number of basis set that you're using through the size of the spectrum that you are solving for. This is a technical point, but this is an important step in the solver portfolio in Siesta. Another example of the Fermi operator expansion is this PEXI algorithm, which is a pole expansion plus selected inversion. The pole expansion looks like this. Now this looks much more complicated, and it looks like a step backwards, because performing an inversion of a matrix appears to be scaling quite badly, again, like cubic scaling. But in fact, we don't need all the elements of these inverse matrices. We just need a few because of the sparsity of the density matrix. So using a very smart selected inversion algorithm, we can get a workable approach, which in fact has reduced complexity, good size scalability. For quasi one-dimensional systems, it can be linear scaling, and even for three-dimensional systems, at most, it scales quadratically with system size. Here we can see a comparison. This is will be the cost of a diagonalization for a given problem, and this will be the cost as a function of the size of the system for this lower dimensional system. So if you have noticed, all the methods I've shown are associated to particular libraries, Scalapack, ELPA, PEXI. And in fact, that's our strategy. These are things that are best done by people who understand what they are doing. And a given code, a given electronic structure or whatever domain code should take advantage of that lower level knowledge and separating concerns and use all the features that people who know how to optimize or how to enhance a given functionality can do, and concentrate on the science. And in fact, we can go one step further. The LC initiative is like a meta library for solvers. It aims at offering an intermediate layer that connects electronic structure codes with available solvers, so that you don't worry about the conversion of matrices, different formats, different options. You give the Hamiltonian and the overlap matrix to the LC layer, select the solver, and then you get back wherever you need, the density matrix or the eigenfunctions, wherever. So we have recently implemented an interface to the LC layer in Siesta with the help of Victor Yu from Duke. And by doing that, we immediately benefit from the further development of the library. For example, you see here a few solvers, in particular ELPA and PEXI are part of LC, and says here many others. And in fact, LC offers, since a year ago approximately, a density matrix purification algorithm that is linear scaling. Now, once you have this LC interface in Siesta, you get this solver for free. You just need to add another line to select it and maybe give a few options for it. Another benefit from using libraries is that you get the benefit of improvements to the performance. And in particular, a very important one is GPU acceleration. This is a sketch of the acceleration obtained in going from using only CPUs in a Marconi 100 computer, which has 32 CPUs per node, and turning on the GPUs, of which this machine has 4 in its node. This is a sketch of the node. You can see that the different stages that we were talking about before in dealing with the matrices in the diagonalization process are accelerated by a substantial amount. So in the end, we get a global speed up of 4 times, or maybe 5 times, depending on whether you count the first step of self-consistency or not. And the good thing is that these enhancements are continuing. I mean, this is not a fixed photograph of, this is just a fixed photograph of what it was the development of these libraries. If the ELPA developers get better kernels, we will immediately benefit from them. And if LC improves the offerings, we will automatically benefit from them. For example, you can see this light blue segment. This is the building of the density matrix once you have the coefficient of the wave functions. up to a few months ago, this step was not accelerated, was not handed over to the GPU, but now it is. So we can get much better performance for this part for free. Another benefit of the separation of concerns. Looking at the scalability of, that is, how well the code performs when you increase the number of nodes for a given problem. This is a picture corresponding to a benchmark for a silicon quantum dot with approximately 35,000 orbitals. Here is the reference diagonalization using only CPUs. Actually, this uses the direct ELPA interface in Siesta. When you turn on the GPUs, you get the approximately 3 or 4 times speed up, and you see, well, a degradation of the scalability when you get to a sizable number of cores. And this degradation has to do with the fact that you're not filling the GPUs with work when you have too many nodes for a given problem size. And another illustration of the benefits of the LC library is this comparison. This looks like a minor thing, but this is a logarithmic scale. This is an improvement using LC over the direct ELPA interface in Siesta, because LC is doing better things, is handing over to the GPU more things and using better data structures. So again, this is a win for Siesta by using appropriate libraries for the diagonalization. But still there is this concern about the scalability. Can we do better than this in terms of scalability? And in fact, we can. Recall that the PEXI solver was based on a pole expansion. It has 3 levels of parallelization. The typical one in Siesta, which is over orbitals, this parallelization over poles, which is nearly trivial, and there is also a more technical one, that is parallelization over trial values for the chemical potential that you are trying to solve for as part of the solution of the problem. It also has a reduced memory footprint because it only deals with the sparse matrices. And it has reduced complexity at most n squared, as I said before. So for example, these are quasi one-dimensional problem, a strand of DNA. And this is a sandwich of graphene and boron nitride. In both cases, nearly 200,000 orbitals. Now, the diagonalization is up here, and it starts at a sizable number of processes just because you cannot fit the problem in fewer processors. Whereas PEXI can do it, and in fact, the CPU time involved is much more. So we did a shootout of methods in high performance computing for very large systems with this benchmark based on coronavirus protein immersed in water. It's about 9,000 atoms and about 60,000 orbitals. This is quite big. And we compare the performance of the diagonalization with and without GPU and with PEXI. Again, you see here the improvement in the diagonalization time when using GPUs, but again, with the reduced scalability. It looks as if it's going to saturate pretty soon here. Then when you use the PEXI solver, you can take the scalability to much larger number of processors. These are 256 nodes, and each node, remember, has 32 CPUs. Another way to look at this is to plot this in a 2-dimensional metric diagram, in which one of the legs is time to solution. This is a very good metric for everybody involved in scientific calculation. You want to get the results faster. But this is also a very relevant one, the cost. You don't want to wipe out your allocation too fast. So here you can see that, in fact, diagonalization is much more efficient in terms of cost, and it gives you a lower time to solution. But if you really want to push it to lower time to solution, you just really use the PEXI solver. Now, these horizontal lines mean almost perfect scalability. There is a jump here because you are starting to put part of your problem in 2 nodes instead of a single node, but that's a technical problem. And also, I should say that the comparison is not completely fair because right now, the LC library, the PEXI library we're using is not GPU accelerated. but work is underway. This is another example of free benefits of using external libraries. So once the PEXI library gets some GPU acceleration, this comparison will be even better. The conclusion to this section is that Siesta has a very, as part of the max effort, has now very efficient solvers, both in terms of scalability for massively parallel architectures for large problem sizes, and also, very relevantly, for acceleration with GPUs, which are a feature of this new crop of machines that are appearing as part of the move to exascale. Thank you very much. Now, I should give the floor to Pablo Ordejon, who is going to talk about an overview of the TranSIESTA module for transport simulations.
Okay, so I hope you can hear me and see my screen. So I'm going to talk about something which is quite particular of Siesta, which is the capability of doing transport simulations in nanoscale systems with a module which is called TranSIESTA. So I'm going to discuss what TranSIESTA does and essentially what are the basic steps to do it in a very basic way. I'm not going to go into details. There's going to be a talk after mine by Nick Papier, who is going to talk about more advanced and newer things. But I'm going to give you just the basics here. And the basics is the challenge we want to do is to compute charge transport in nanoscale devices, nanoscale systems, very much the same way that we are able to compute very easily and very traditionally the charge transport in electronic devices in the macro scale, like a resistor. We have Ohm's law that tells us how to compute the current from the voltage and the resistance. We want to do the same in the field of nanoelectronics or molecular electronics, where the devices are very small, are molecular size or nanometer size. So in this particular case, I'm showing you two metallic contacts which are contacting a molecule. You can put a voltage between the two metallic leads and some current will flow, and you want to know what is the current or what is the resistance or conductance of the device, of the molecular device that you have in your electrodes. How do you do that? It's quite complicated in many senses. We need basic understanding of the transport phenomena in nanoscale materials and devices. And that entails, first of all, to deal fully with the quantum effects. Quantum effects are essential. You have very small molecules or contacts, which means that you have quantum confinement. You have discrete levels of energy compared to the continuous metal levels of energy in a bulk metal or semiconductor. And you also have ballistic conductions in the sense that the mean free path of the electrons in the molecular device or the nano device is very short compared to the scattering times with phonons, with electrons, and with defects. So you truly have fully quantum effects that you have to take into account. You cannot do this with semi-classical approaches like the ones you deal with classical electronic devices. Now, we also want to do it in atomic detail. When you change one atom in a molecule like this, the whole thing changes, the whole resistance can change. So we want atomic detail. And we want to do it from first principles, which is what Siesta does. So for that, we developed a number of years ago, almost 20 years ago, a module for Siesta, which was called TranSIESTA. It's still called TranSIESTA, which performs these quantum transport calculations fully from electronics, from density functional theory, from first principles. So there is no parameterization here. And this is the basic reference published in 2002, so quite old paper already. But there are some new papers, in particular one that Nick Papier and co-authors published a couple of years ago with the revamping of the code and new methods which are much more efficient and much more advanced. And that will be the topic of the next talk. So how can you compute a physical property like a resistance or a conductance in such a small device? The basic idea is the following. When you put a battery between the two electrodes, essentially what you are doing is to shift in the Fermi levels or the chemical potentials of the left and the right metallic lead. So that creates an imbalance, and you have a portion of electrons from the left electrode that could go through the molecule and go through the Fermi sea of the right electrode, because these states are empty. And what you have to calculate is exactly this current of electrons going from this region of the Fermi sea to the right region of the Fermi sea. How can you compute that? What you do is computing conductance as a scattering problem. You have electrons that come from the left electrode that arrive to the barrier or to the molecule or the constriction. Part of the wave functions becomes reflected back to the bulk of the material of the electrode, but part of the wave function gets transmitted through the barrier and goes into the metallic lid on the right, and that creates a current. So you have some net current going through from the left to the right. And the current can be computed by a very simple formula, which takes into account this transmission matrix, which is the matrix that relates the incoming wave with the outgoing wave on the right, with this T matrix. If you compute the trace of this matrix and as a function of the energy, you have what is called the transmission coefficient. And the current is very simply the transmission coefficient multiplied by the difference in the Fermi levels of the left and right electrodes. In other words, this window from one Fermi level to the next one. Okay, so this is a very simple integral. If you know what is the shape of this transmission energy, which is just a function that you can calculate, you have the current. And with the current, of course, you have the resistance too, if you know the voltage. And this is what is traditionally called the Landauer-Büttiker formulation of conductance in nanosystems as conductance as a scattering. So how can you compute that in a code like Siesta? Well, you could in principle compute the transmission matrix like a scattering problem, but that's really quite complicated, and we do it in a very different way, which is much more efficient and appropriate, which is using Green's functions. And just a very short detour on the Green's functions. You have a system like this one, which is an open system. You have your nanoscale contact through which the current is flowing, and you have a left and a right electrode. The Green function of this material or this system is just energy times the unit matrix minus the Hamiltonian, all the inverse of this matrix. And in this particular case, it will be the inverse of an infinite matrix because the left and the right electrodes are infinite bulk material. So this matrix will go infinite and will go forever. You have the coupling, the energies here in the central region and the couplings with the right and left region. But then in the right and left region, you have semi-infinite matrices here and here. So that's something that you cannot compute in practice, but there is a very, very nice trick, which is to set everything up only in a region around the center, the contact, the nanoscale constriction. So you take into account only this small section of a space, and you assume that on the right and the left, what you are left is with purely bulk electrodes. So here the electronic structure and the Hamiltonian will be the same as the bulk electrode. So you can do that if this contour is deep enough into the bulk of the electrode. And in this particular case, you can see that the Green's function can be computed solving this finite matrix, which has the size of the contact region, of the number of orbitals in the contact region, and all the effect of the right and left electrodes are given by these matrices here, sigma L and sigma R, which are the self-energies of the two right and left electrodes. And this can be computed very easily if you know the bulk functions of the bulk right and left electrodes, which are very easy to compute because again is the inverse of the Green's function of the Hamiltonian in these regions. So that can be done very, very easily and very efficiently. So with this, you can just, by inverting a finite size matrix, which is perfectly doable, you can get the Green's function of the contact region. And from that Green's function, you can get exactly what you need for transport. You can, for instance, compute the transmission matrix, which is going to be just the Green's function in the contact region, multiplied to the left and the right to what is called the coupling matrices, which is just the imaginary part of the self-energies. So again, having the self-energies of the left and right electrodes and the Green function of the contact, you can have the current. And that's a very easy thing to compute. You can also compute something which is a bit more difficult to compute, which is the charge density. You are doing density functional theory. So to compute the Hamiltonian, you need to know the charge density in all the atoms on your contact and your electrodes. How do you do that? It's not so trivial because in this particular case, you have a bias between the two electrodes. So you have two different Fermi levels. So how can you compute the charge density, if you have two different Fermi levels, you don't know how to fill the electronic levels, because for that, you need to know up to which level you are filling out. With this trick of the Green's function, you can use what is called non-equilibrium Green's functions, or the Keldysh formalism, that tells you exactly how to do that. If you know the Green's functions and the self-energy, you can compute the density matrix just by filling the states that come from the left electrode with the Fermi level of the left electrode, and the states coming from the right electrode with Fermi levels of the right electrode. So you have to compute two energy density matrices, which again have to do with the Green's functions of the left and the self-energies of the left and the right. So these are all things that you can calculate if you have the Green's functions. And this is exactly what TranSIESTA does. So to do that, you need to set up your system appropriately in TranSIESTA. And let me give you the basic steps to do it. The first thing you have to do, of course, is to set up your molecule, the coordinates of your molecule or your nano device, your nano contact. Then you have to attach a few atoms that contact the molecule with the left and the right electrodes. In this case, it's a pyramidal shape of cold atoms in this particular case. Then you have to attach a few layers of your left and right electrode. And this number of layers has to be sufficiently large, because all the screening created by the molecule in the bulk metal has to be taken into account within this region. So in this particular plot, I just put two and one on each side, but this is not enough. You would need to have a few layers so that the screening is completely taken into account. And then what you do is you link that with bulk electrodes at the left and the right, which are just purely periodic bulk crystal electrodes for the left and right electrodes. And these electrodes are not considered in your calculation. So your contour calculation, your contact is going to be this region here, and you are going to invert a matrix of this size. But you will take into account fully the physical effect of the left and right electrodes by the self-energies that you have to compute from the bulk calculation a priori. So again, wrapping up, you need to consider the molecule as a defect, in the sense that this defect has some effect in the electronic structure of the left and the right leads. And you have to make these regions in the left and right large enough so that all this screening is taken fully into account in this region. So you have to ensure that the electrodes at the left and the right behave really as bulk electrodes. You need a previous siesta run to compute the bulk electrodes and the self-energies. And then the siesta calculation, the TranSIESTA calculation, is done by inverting the Hamiltonian in this region of space only. So that's a finite size region. A particular technical point here is that in the direction perpendicular to transport, so in this direction and the direction perpendicular to the screen, TranSIESTA usually assumes periodic boundary conditions. So actually you are computing a periodic array of this molecule repeated in space. Nick is going to tell you about how to avoid that and do really a single molecular contact with the new versions of TranSIESTA. Okay, so just a couple of examples as a matter of showing what kind of things this can compute. Let me show you the very first application we did with TranSIESTA, which was to study the conductance of monatomic gold wires. That's something that you can actually build experimentally. You can build wires with different number of atomic cross sections from, in this image, from 4 to 3 to even to 1. And when you reach the size of 1 atom thick, then the conductance is what is called 1 quantum of conductance, 1 in the units of this number here, 2e squared over h. And that happens always that you have a 1 atom thick wire. So you have these histograms when you have this very nice peak of conductance around 1. And that was one of the first calculations we did with TranSIESTA. We set up systems like this. This was one particular case just with 3 atoms of length, but 1 atom of width. And you see that the transmission energy curve that I was mentioning before, in this particular case, near the Fermi level is very close to 1, which means that the conductance is going to be 1 quantum of conductance. So this was a very nice application showing that this code could really explain the experimental observations in this particular system. Since then, we have done many calculations in this with this code, and I'm just flashing you a few here. For instance, Emilio was showing before calculations of Siesta with DNA, and we have applied TranSIESTA to compute some of the transport properties of DNA. For instance, this is a case in which 2 nanotubes are used as electrodes, and you steer how much current is through in the, across the DNA chain, which depends on the specific sequence of bases which you have in DNA. So you could use this resistance or conductance measurement to determine what is the sequence of the DNA chain. And the same thing you can do by passing a DNA chain, or in this particular case, it's a single strand through a nanopore in graphene. And by looking at the current that you generate in graphene with a voltage between the two sides, that current depends on which base is going through DNA, and then you can also sequence the DNA chain with this method. But we have also used it for electric wires. So if you want to use a nanotube to connect 2 graphene devices, you can, with TranSIESTA, determine what are the properties of conductance of these contacts, or something much more general, which is Stm Imaging. So you have a tip that you put on top of a material. In this particular case, it's a surface when you have a fullerene molecule and some complex organic molecule. This is also a transport problem because you put a difference in voltage between the tip and the sample, and some electron current is flowing. And you can, with TranSIESTA, you can even image or simulate the images that you will measure experimentally with the STM tip. And I think Nick is also going to show an example of that in his talk. And that's all I wanted to show you. Thank you for your attention. And if you have any questions, I'll be happy to answer. So let me give the floor to the next speaker, which is Nick Papier. He's from DTU in Denmark, and he's going to talk about performance optimizations and new functionalities in TranSIESTA.
Hello, do you hear me? Yes, I think so.
Yes, yes.
Thanks. So thanks, Pablo. And I'm going to continue talking on the latest improvements of the TranSIESTA code, in particular some performance optimizations and also some new functionality. So here's a list of the new capabilities of TranSIESTA, and on the slides you'll notice these all around, and these are the DOIs of the papers that you can check out for more details. So first of all, the latest TranSIESTA version enables any number of electrodes and also one electrode if so wished. So for one electrode, it's a pristine surface, and for anything more than one electrode, you can apply biases and have particular different Fermi levels. And you can have any number of different bias levels or different chemical potentials. And also for the chemical potentials, you can both define the chemical potential, and you can also define a temperature of the electronic population. TranSIESTA also offers a much improved inversion algorithm, or 2 other more performance versions, and that leads to a capability of calculating much bigger systems. Emilio also showed you this system in the first presentation, and that's, I think, around 4,000 atoms. So you really have a capability of doing big systems now. A very new implementation is the so-called real space self-energies, which allows us to do true surfaces and true single defect calculations. As Pablo was mentioning, you were still having a transverse periodicity in the regular TranSIESTA calculations, but now we have implemented ways to circumvent these problems. You can also add gates, and you can add gates with complex shapes. In this case, you have a gate plane, sort of a capacitor-like setup, and you have the atomic system up here. This allows you to put a capacitor field between these 2 sheets of charges, and allows you to do complicated stuff with that. You can also do this in combination with TranSIESTA. It's not only Siesta part that you can do this. And if you do that, for instance, for graphene, as in this case, you see some weird effects, which I will cover in the next slide. Yeah, so charge gates. So you can add, there are many ways of adding charge gates. And in this example, you'll just have a flat planar gate, and that's a perfectly fine way of doing it. But you can also add spheres if you want to mirror an effect of a charge gate or a charge defect in some of the systems you want. Then you can add a specific sphere of a certain charge, which mimics or mirrors that of the induced charge in your system. You can also do boxes of charges if you have a, say, more charge over in this area of the field and less charge in the other one. And it's all up to the user how to define and where to have these kind of gates. One way of, one thing you can use this for is to calculate the decay length of the charges in a specific slab. In this case, it's a graphite slab of 12 layers of graphene. And you'll see that when you have a gate down here, disconnected by 20 angstroms, you can actually calculate that the decay length of the charges is around 2.4 angstrom. And that goes very well with some experimental values. And you can do this for many other systems. What we have also done is to use this for graphene, a graphene constriction with a gate capacitor. And here you have pristine graphene in the TranSIESTA calculation up here, and then a small constriction, and then pristine graphene down here. And when you just do a regular graphene calculation with applied bias for this kind of systems, you actually end up in a very weird situation because of the Dirac point of graphene. And the Dirac point of graphene is very sensitive to small changes in the charge distribution. So you really should be careful of what you're doing. But as soon as you have a gate, you actually shift the Fermi level of the corresponding electrodes, and that leads to a difference in the density of states at the Fermi level. And this is actually what causes a pinning of the potential drop, which pins it to one side of the constriction depending on the polarity of the bias that you have. And this pinning of the potential you cannot find if you don't have a charge gate underneath this one. And now on to the matrix inversions or the performant part of the TranSIESTA. So TranSIESTA is relying on this inversion that Alberto was showing, and also Pablo was showing the full equation of this one. And this is the problem. It scales as n cubed, and it's really not efficient to do this inversion in the dense form. As Alberto mentioned, the PEXI way of doing it, you only calculate the elements that you need. And it's the same thing with TranSIESTA. We don't need the full dense matrix of G. You only need where you have the density matrix elements. So you can do sparse inversions, and you can use PEXI, or you can use MOMS. And there are many other ways of doing it. And another third way of doing it is the block tridiagonal inversion. And this is what we have implemented in TranSIESTA, which seems to give the best performance for a large variety of systems. So the block tridiagonal inversion algorithm is actually very simple. You have any kind of matrix that can be expressed in this form, with a diagonal, and then a small upper diagonal and a small lower diagonal. And then all in the upper right corner is zeros, and all in the lower left corner are zeros. And then you just follow this procedure with some temporary matrices X and Y. And when you've calculated these, you can actually calculate the entire inverted matrix. This turns out to be way more efficient because you in TranSIESTA, you don't really need to calculate anything other than the G of where you have A, B, and C matrices. So here's a small test comparison with the previous TranSIESTA versions. So TranSIESTA now implements 3 different inversion algorithms. Dense matrices, which is basically the same as the old version, sparse inversions, and block tridiagonal inversion. And here you see for a zero bias calculation, you find for an increasing size of the system that you see speedups of around 50 to 60. And this is all depending on the width of the system, because the block tridiagonal inversion depends on the matrix sizes in the sub-blocks of the matrix. And if you do a bias calculation, it turns out that it's even faster, and you see a huge performance increase. Now here you will see that the sparse matrix MUMS is not as efficient as the block tridiagonal version. In this case, the system is narrow, but in some cases, when you have a very wide system and not that long a system, MUMS may provide a better performance, at least for the zero bias case. For the biased case, it's not particularly good for other reasons that I will not discuss here. So you can easily get a factor of 100 depending on the system you choose. Another method that has been implemented in TranSIESTA is the threaded version. So you can now do both MPI and OpenMP threading. And every time you double the number of threads you use, you will halve the amount of memory you use in TranSIESTA. So you can really go to really big systems. And the system I showed you in the first slide of this around 4,000 atom system that uses threading. So you can really scale the system. And here is just a speed up curve of how the threading performs. And this follows pretty well Amdahl's law of what we suspect it to do. And then another detail of this removing all periodic boundaries. As Pablo mentioned, you have the transverse periodicity, and that is really not desired. So what you do for a regular siesta calculation is in fact that you have some kind of bulk part out here, which is shown or highlighted by the grid, and then you have some defect by this red blob. In a regular siesta calculation, what you really have is periodic boundary conditions all around, so it will see its mirror defect all around for all cases. Now what you can do is you can do this for TranSIESTA, and that will remove periodicities or the images along one axis. So you'll still have some periodic images transverse to the self-energies of your left and right electrode. And that was what Pablo was referring to. And that can turn out to have some problems because you have some interference effects depending on the distance between the two defects in the supercell approach. And this paper highlights this problem very nice. And yeah, okay, so let's move on to how you can do this. What you really want to do is you want to put a self-energy of the bulk infinite part around the defect. That will ensure that this one defect has no coupling to its mirror it mirror defects. And the way to do this is by this simple equation. It is really quite simple. The problem is that it's quite heavy to calculate because you need to do a fine integral of the Green's function for every energy point in the Brillouin zone. So here the problem is that the Green function calculation scales as n cube. Here we really need to calculate the full Green function, so it's probably easier to do the dense matrix form. And then the size of the Green function that you want to calculate is the full thing here. So in this case, you would actually want to calculate the full Green's function for a system that really has this size, because you really need the proper couplings between the Green's function elements. And in particular, this provides that is actually the problem of this method, because you really need to do big matrix inversions, and you need a very fine integral in the Brillouin zone to get a good real space Green's function, and thus a good real space self-energy. So you cannot really do with more than a few hundred orbitals on a regular basis if you do this in the dense form. So in this paper, we have devised a method to do this very efficiently, and I will now show you what you can actually do with this. So a case study is a nitrogen defect in graphene. And what you typically see, this is an experiment up here in the left image, and on the right image, you'll see a simulated image of the corresponding unit cell. This unit cell is a 9x9 system, so it has 162 atoms. And what you'll see from the band structure, here you have the green marks highlight the nitrogen defect. You'll have a split density of states on the project density of states on the nitrogen. So you'll see a two-peak structure in the density of states when you project it onto the nitrogen. But that is in fact not the true case. You have a single nitrogen, and that has no dispersion because it's a lone defect. So what you should see is, in particular, a one-peak structure, and it may have a long tail, but you should see a one-peak structure. So here's a comparison between siesta and a regular TranSIESTA calculation with 2 electrodes and a surrounding self-energy or real space self-energy. Here you see that the green curves, the green dash curve is the Siesta one. This one has 2 peaks, but that's due to the periodicity of this square lattice. In the previous calculation, it was the hexagonal lattice, and then you only see 1 peak. So that depends on the system cell that you're using. If you then use the TranSIESTA calculation, you see a 2-peak structure, but that's also wrong, because you still have the periodicity in the transverse directions. When you then find the true calculation is when you do the real space self-energy. You find a 1-peak structure and a broad tail that encompasses. In general, they seem to correspond very nicely, but in particular, the real space method captures the real density of state of the nitrogen in the best way. This is also consistent with large-scale tight binding calculations, where you also only see 1 peak. As Pablo also mentioned, there's the Stm study, and Stm is used for many case studies, and it's a very nice technique. The problem with that in TranSIESTA is that you really need to have a single Stm tip, and you never have that, so you have interference effects. And that can prove quite severe in the calculations you do. And here you have a calculation between a TranSIESTA 2 tip, a 3 electrode TranSIESTA calculation and a 2 electrode calculation. So the top gray one has a left-right graphene and a tip electrode. The red one has a surrounding self-energy on the blue atoms and then a tip electrode up here. And you'll see a huge difference between these 2 curves, at least for the unoccupied space. Another thing is that when you plot the bond currents in this case, you can really see the effect of the interference effects. So here you have a left-right, so you have 3 electrodes, and here you have the real space self-energy. So the interference effects here, so here the neighboring tip is up on the, what can you say, the north side of the plot, and that kills off the actual path that you will see in a correct calculations. If you do a really big tight binding calculations, what you'll see is a 6-star shape of the injected current from the tip. That's the true calculation that should give that result, and that you will find by using a real space self-energy. Another thing that this can be used for is to calculate surface states. So again, in the TranSIESTA calculation, when you have periodic boundary conditions on the transverse parts, you will have a mirror of the Stm part. And that will cause the surface states to disappear in the calculation. You actually cannot find them in the calculation if you do it in this way. But when you do the real space self-energy, you have a single tip, and then you can capture the surface states because you don't have any defect that destroys the surface states. And here's this is a problem that we have been working on for some time now, and this will hopefully soon be submitted. And what you will find is that when you do the regular TranSIESTA with 2 electrodes and transverse periodic boundary conditions, you'll find a black curve here. So there you don't have any surface states. But when you do the real space self-energy, you actually get a increased transmission just below the Fermi level, and that corresponds very nicely with the binding energy of or the energy that corresponds to the surface state. And the problem is that here you first of all, in the periodic boundary condition calculations, you don't really get the surface state due to the interference of the Stm tips with itself. And here you can really also absorb the electron in the surface state. So here you cannot really figure out where it actually goes, the electron, but you just know that it goes somewhere along the surface or in the bulk. So in conclusion, there's a huge memory reduction and a performance improvement in the TranSIESTA calculations that enables you to do really big systems. It scales to many more cores due to threading. So TranSIESTA is still only parallelized over energy points. But if you employ threading, you can really go beyond this for a really large scale calculation. You can do now true N electrode calculations, also one for proper slab calculations, and you can do gate configuration to simulate capacitors and applied biases and stuff like that. We also have this efficient calculation of the real space self-energies that allows you to do single defect calculations, which is, if you have concerns of interference effects, this is the correct way to do it. And by that, I will acknowledge the the people who actually did most of the work, and then also announce a coming workshop on the TranSIESTA TB Trans workshop that will be held in May 17 to 21, and that will be a virtual workshop. And other than that, thanks for the institutions that have been funding this, and I think that's it. So I will give the floor to Monica. Thanks.
Hello, so I'm Monica Garcia from Simune Atomistic Simulation, and today I'm presenting some recent activities related with the user support for Siesta, such are the ones related with mass user support activities, some recent actions coming from the Siesta community, and also some activities from the company Simune. So in mass, there is a strong interest on offering support for the material science community, and they offer support for mass code and beyond, and also high-level consultancy. In this link, you can find further information about mass services. And here you have a list of the mass code, the list of the mass codes. Well, this slide is only to give you some examples of mass support actions. And I want to say that mass offers support in two different ways: by its code community via forum and mailing list. As you might well know, there is the Siesta mailing list where you can put your questions and answers. And also they offer support via the mass help desk operated by Shineka. Here in Simone, we share mass interest to support the material science community and the development of open source codes. And Simone was launched in 2013 as a joint venture of developers of Siesta and Codes and thick Nanogune. And I will tell you later about our services and products. But now I just want to present Simone as the bridge between the academia and industry, because we have collaborators in both environments. In particular, today I want to tell you about a recent project, Siesta Pro project, that in this project, Simone invested 5 million euros, and the project was in collaboration with 3 partners that are from the Siesta community. And thanks to this project, the software structure quality and functionality quality has been improved, also the usability of the Siesta code. And we also launched a forum that I think that is of interest of the Siesta community. So I will say a few words about 2 of these topics, that are the migration to Gitlab and the forum that was recently launched. The migration from Launchpad to Gitlab, it happens like 1 year ago. And it was necessary due to the fact that the Bazaar version control system was not longer supported. So now this is the place where you can find the Siesta code, the issues related with Siesta, merge requests, and so on. And also, I want to tell you that here there is a wiki where there is hosted relevant information for both users and developers. So here you can find Siesta manuals and tutorials, information of stable, beta release, and development branches. And also, so to learn how to start with Git and Gitlab, some guidelines to contribute to Siesta code. And I can tell you that in the future, in the short future, there will be other relevant topics hosted in this wiki. So then, as I said before, within the Siesta Pro project, we launched a forum. Here you can post your questions related to the use of the Siesta code. This is an alternative to the Siesta mailing list. In fact, so we are summarizing the most relevant question and answer from the Siesta mailing list in the forum. the difference is that here the topics are, the different questions and topics are classified in categories. So here you have the link to the forum. Okay, so now I want to say a few words about the Simune services. So as I said before, so we are recent companies and we offer material consultancy services. We support the development of open source codes. And we also offer support for the use of Siesta. So, and I will tell you later about the product ASAP, the Atomistic Simulation Advanced Platform, that it facilitates the use of the submission of a Siesta code and its analysis. So I want also to tell you that in Simune we have generated binaries for Unix and Windows systems. We also have Docker images for Windows, Linux, and Mac, that all of them are accessible from Simune webpage. So you can request their Siesta binaries and Siesta Docker. Also from our webpage, you can download a limited set of pseudopotential and basis set. They were generated and optimized by Simune and validated. And these are PSF pseudopotential. Of course, if you are interested in using there are PSF pseudopotential. Sorry, if you are interested for PSML pseudopotentials, you are welcome to look at the Pseudo-Dojo webpage. So finally, I want to introduce you ASAP, Atomistic Simulation Advanced Platform. As I said before, this is a user-friendly graphical user interface that facilitates the complete submission and analysis of a Siesta code. So you can set up the system, the project parameters, the calculator that is interact with Siesta, run the simulation and analyze the results. I invite you to request an ASAP trial version from our webpage, and then you can try the different ASAP components. For example, the atomic structure builder to build your system, so surfaces, bulk, and molecules. Then you can also create your FDF input file using the graphical user interface for the Siesta calculator, that it contains different Siesta parameters. Then you create the Siesta input file and you can customize it later. And also there is analysis widget where you can analyze the Siesta output. For example, I'm showing here the density of states. So thank you very much for your attention, and I will be very welcome to answer your questions.
Okay, I guess you can hear me. So this is the end of the webinar. We have been answering some questions in the question and answer bit, as many as we could. If there are other questions you would like us to answer now. So there is a question on hybrids at the moment. And so there has been an implementation of hybrid functionals in Siesta. It's quite recent. It was done within the Siesta Pro project that Monica was discussing before. And it is described in the Journal of Chemical Physics paper that came out a few months ago, 2020, the one led by Alberto Garcia. You have a description what it does there so far, and I think that it is not merged into the trunk of Siesta yet. But
if I can intervene, yeah, the source for this feature is not in the main GitLab repository. We are preparing a version that can be shared with interested people on demand. They should write to us, and in particular to Javier Junquera, who is the leading developer of this.
Somebody is asking about whether one can rewatch this this seminar actually. So maybe Francesco, do you know how that can be done, or whether that can be done?
Yes, this is a very good point. Thanks, Emilio. I was about to write in the chat, but I take this opportunity to say that by tomorrow you will be able to have the recorded webinar session in the Max website in the specific web page of this webinar, and probably by tonight you will be able to find your presentation slide as well.
There is a question about Simune that maybe Monica is the best one. So the question is by an anonymous attendee. Is Simune free?
Okay, I can clarify this. So Simune is the name of the company, and the software that I was talking about is ASAP, that is a commercial software. So we offer a trial, but the software is commercial. But so we integrate open source code, but it will be with the Simune license, the software.
But Simune has also offered some services that are, so there is support offered by Simune through the forum, and other services that have been for free, for instance, things done for pseudo potentials and basic.
Exactly, yeah. Yeah, the pseudo potentials, the Siesta binary, and the Siesta Docker, we are offering for free to the Siesta community.
Okay. So that also answers another question, whether there will be an academic version of ASAP. And I don't know whether that's the plan, Monica?
Yeah, this is the plan. So, I mean, it will be a license, not academic, so the software, it will be always commercial, but with an academic license and a license for industry.
Any other questions you may have? Or any of the panelists, if they have seen any questions they would like to answer or to expand on.
Yes, there has been a request for binaries, precompiled binaries. And this is part of a larger issue, which is the building of Siesta, with the push to use many libraries. Of course, the compilation of the code is no longer as easy as it used to be. And we are working on two fronts. One is to provide as much as we can with good documentation, although the idiosyncrasies of computer centers and machines are very difficult to deal with perfectly. And the second is to provide new technologies like Docker, containers, and pre-built binaries, or even distributions like Ubuntu and Conda-Forge, things like that. All this is being worked on. This is a major priority for us, and we request your patience because it's going to be great once we figure it out.
Okay, there has been another question on training, and there are plans for Siesta schools, Siesta and TranSIESTA schools separate, that have been regrettably postponed because of the pandemic, but in 2021 there should be things coming up on this front. There has also been a question on the possibility of training with us and also of collaborating with us. And I had a tentative answer in the written question and answer bit, in which essentially that kind of thing goes. We are active researchers in science, and so having people coming to collaborate or collaborating with people goes in the traditional way as we do collaborations in science, so finding support and finding topics of mutual interests. So the wider spreading of the use of Siesta goes in terms of formal training, either in schools or seminars and so on. Any other question, or anybody else of the panelists that have spotted anything they would like to expand upon? Okay. So there's another question on the possibility of doing time-dependent DFT calculations with hybrid functionals. The answer is not yet. Hybrid functionals, they have been very recently implemented, so the interaction of, Alberto is going to answer that. I just see. So Alberto, if you want to.
No, I just clicked that because you are answering live.
Oh, I see, sorry. Hiccups of these technologies. So in principle, that is the interaction of relatively novel aspects of the code with other aspects of the code sometimes takes a bit longer. So the propagation of time-dependent DFT with hybrids hasn't been done yet. If it's time-dependent DFT in omega, I think that is a completely different question, and I'm not qualified to answer that. So then there have been other questions about transport with spin. Maybe Nick or Pablo can say something about that. Hello.
Oh, sorry, I answered it live in the QA.
Okay,
so yeah,
that's fine. So there is another question on possibilities of internships, and that goes a little bit in the direction I was talking about. So internships and stages and internal training goes in the direction of research collaboration rather than
I can say that from Simone, we are also very open to new collaborations.
Yeah, and there are different sources of funding for that kind of thing. It depends on countries of origin or different programs and so on. So typically, for instance, within Europe, there is this HPC Europe channel for getting funding to go and do train in supercomputing softwares of different kinds. So that could be a possibility. So how is Siesta comparable with other LCIO codes like Conquest and Openmx? Okay, so Conquest as such started as a non-LCIO code. It was based on support functions that were expanded on blips that were supposed to go in the direction of a real space analog of plane waves. So it was a much more systematic basis set. But of course, that if one goes to that kind of basis set, Conquest in that sense would be somehow similar to OneTep. But Conquest then also offered the possibility of doing LCIO within it. And as far as I've talked to some of the developers, Dave Bowler and so on in Conquest, the basis sets used in Conquest should not be too different from the ones in Siesta. Although, of course, quite a lot of the technicalities within are going to be quite different. So I have never used Conquest myself. Openmx is an interesting thing. Openmx is a code which was developed completely independently from Siesta in Japan. But the basic method is very much the Siesta method as was developed. So it's taking the ideas of the Siesta development, of the Siesta method itself, and it's a complete different implementation. And some of the choices for basis sets have been different and so on. And again, I never used it, but it seems like an interesting code as well. And other LCIO codes, there are so many that I cannot respond more generally than that. Okay, so the spin has...
So Emilio?
Yeah.
Sorry, I'm Francesco, and I regretfully have to wrap up because we are running out of time. I want really to thank all first of all the audience, all the people that join us today, and you all speakers that made a tremendous job in your presentation. I just wanted to ensure that the people that saw their question dismissed, that we are going to go back to you as soon as we can, and you will find the response to your question in a Max webpage again. So again, I want to thank you really warmly, and thank you for being here. The next Max webinar is going to be next 14th of October. It's going to be on Fleur code, and I hope to see you there very soon. And take care, all of you. Thanks again, and have a good evening. Goodbye.
Bye.
Bye-bye.